Today we're going to start our lesson on oxidation and reduction. And so today I'm going to tell you what oxidation and reduction are and how we can assign oxidation numbers. So let's start with some definitions. So in an oxidation reduction reaction, we have electrons being transferred from one substance to another substance. Okay, and it's composed of an oxidation and a reduction. So an oxidation is the loss of electrons. So one thing in the reaction is going to be oxidized, it's going to lose electrons. And then the reduction is the gain of electrons. So something else in the reaction has to gain electrons in order for us to get an oxidation reduction reaction, because we can't just create electrons or lose them out of nowhere. All right, and then there's a little acronym which is also given in your book, which is oxidation is loss and reduction is gain. All right, oil rig. And then there's another one that you could see from the first slide, which is Leo, the lion, says GER, and LEO stands for losing electrons, oxidation, sorry, and GER stands for gaining electrons, reduction. So those are two different ways you can maybe remember which is oxidation and which is reduction. Okay, and then below here I've written two what we call half reactions. So this is where we have the oxidation and the reduction written separately. So here you can see that zinc, which is a solid, it loses 2 electrons to become zinc 2 plus. So right, if it loses 2 negative charges, it now has a positive 2 charge. And copper, in this case, starts as an ion, so copper 2 plus, and then it gains 2 electrons to become a neutral copper atom. So if we were to add these two together, the electrons would cancel out and you'd get your oxidation reduction reaction as the sum of the two half reactions. In order to keep track of where the electrons are moving in a reaction, we use a concept called oxidation numbers, or sometimes it's referred to as oxidation state. All right, and these are just assigned based on the set of rules that I'm getting ready to talk to you about, but it basically gives us an idea of how many electrons are associated with a particular atom if it's in a compound. So if it's by itself, it's really easy. So for rules for assigning oxidation numbers, you can see that the oxidation numbers have to add up to whatever the charge is. So if it's a neutral molecule, all of the oxidation numbers in the molecule have to add up to 0. And if it's an ion, a polyatomic ion, they have to add up to whatever charge that ion has. All right. If we just have a single element, like we did on the previous slide with the zinc or copper, then if it's just a single atom all by itself, or if it's diatomic, something like H2, and it has no charge, then the oxidation number is 0. All right, if it's a single atom that's an ion, then the oxidation number is its charge. So when we had zinc 2 plus on the previous slide, the oxidation number for that would be +2. Okay, in compounds, the oxidation number of group 1A metals is +1 and group 2A metals is always +2. All right, and this should be familiar to you because that's the charges they take when we assign charge in ionic compounds. So group 1, which is the first column, always has a +1 charge, and group 2 always has a +2 charge. So there's a strong relationship between oxidation number and charge, especially in ionic compounds, but in molecular compounds it gets a little more complicated because, as you know, the atoms in those don't have specific charges. All right, and then in compounds where the oxidation number of fluorine if there's a fluorine in the compound, the oxidation number of fluorine is always -1. And generally, other metal or other nonmetals in that column are also -1, but not if they're combined with oxygen or fluorine. Okay, and we're going to do some examples which will make these rules a little more clear, I hope. And then number 6 is in compounds, the oxidation number of oxygen is -2 unless it's paired with fluorine. Okay, so like in OF2. And in compounds with nonmetals, the oxidation number of hydrogen is always +1 unless it's like H2 where it's by itself, and except in compounds where it's with a metal, and then it's -1. Okay, so we're going to go through some examples of this, so hopefully you get a good sense of how to assign these oxidation numbers. Okay, so the first example we have here is NCl3. And on the previous slide in the rules, it said that nonmetals in group 7A, which is the column with fluorine, chlorine, bromine, and iodine, that they are always -1 unless they're paired with oxygen or fluorine. But we don't have oxygen or fluorine here, and there's nothing in the rules about nitrogen. So what you're going to learn is that for molecules, when we have nitrogen or carbon, they're going to take on whatever oxidation state makes the charge for the whole molecule work out right. So we're going to assign the chlorine a -1, but we have 3 of those, and then we don't know the value for the nitrogen. We're going to call that x. So we have x plus 3 times -1 has to equal 0. Okay, this is a pretty easy algebra problem, and you should see that x has to equal +3 in order for this to be neutral. Okay, so now we've got oxidation numbers for both of the elements in our molecule. Right, now we have a polyatomic ion, so we know this is going to have to equal to -2 when we add all of them up. We know that oxygen is always -2 unless it's got fluorine with it, and this does not. All right, so we have 3 times -2 plus x, because we just have one carbon, has to equal -2. All right, 3 times -2 is going to give us -6. If we add 6 to both sides, we get that carbon must be +4 in this particular compound. Okay, and you'll get better at doing these in your head, but I encourage you to write out the algebra at least when you're getting started. Okay, so number 3, now that we know how to assign oxidation numbers, we can determine in an equation what's oxidized and what's reduced. Okay, so here we have CO2, so and there's no charge on that molecule, so oxygen is -2, and we have 2 of those, so that's -4. So we know the carbon must be +4 in order to make that neutral. Hydrogen is all by itself with no charge, so both of those hydrogen atoms must have a 0 oxidation number. Right, on this side we have carbon and oxygen, and we just have one oxygen in this case, so one oxygen is -2, and to make the charge of that 0, the carbon must be +2. All right, and then here for water, we know that the oxygen is -2, and each of the hydrogens is +1, so 2 times +1 plus -2 gives us 0, so that works out okay. All right, and now you can see that the oxidation number of the carbon and the hydrogen both change. So carbon goes from +4 to +2, so that means the charge goes down, which means it must have gained some electrons, so that's a reduction. Okay, it takes a little while, a little bit of thinking through this in order to get comfortable with it. All right, and then hydrogen goes from 0 to +1, which means that the charge went up, which means it must have lost an electron, so the hydrogen is oxidized. Okay, and we will do lots of practice with these, and hopefully you'll get really comfortable with assigning oxidation numbers and then determining what is oxidized and what is reduced.